Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture number 30 in the course Advanced Robotics. In the last class we looked at bipedal locomotion and then we talked about optimization of bipedal gait. That means whenever you have a redundant system like a bipedal robot where you have 8 degrees of freedom or more, you always tend to have infinite solutions. For example, you can walk with infinite feet trajectories. So in such cases, you have to do some kind of optimization. In that case, we saw that you are talking in terms of energy optimization, that we should choose a gate which is going to minimize the energy. Today, we'll look at other robotic systems like multi-agent systems, okay, where, for example, multi-agent system can be multiple mobile robots which are catching an object, pushing it somewhere, or even the case of our multi-fingered hand. So if I look at an object like this and I have multiple fingers and I'm going to move it around like this, then each of this can be considered to be a serial manipulator. So these are multiple robots or multi-agents which are catching this object and moving it in some direction. Okay, so this is what we mean by multi-agent system. And in such cases, we need to optimize in terms of what is the minimum number of robots required, what is the best position around the object, what is the best pushing strategy, and things like that. Okay, and then we'll also talk about bipedal locomotion in 3D. In the last class, we talked about bipedal locomotion or optimal gait on flat ground. But if you're going in three-dimensional terrain and there are obstacles, how are you going to avoid such obstacles? And how can you actually get optimal gait in three-dimensional terrains? Okay, so today we're talking about optimization in motion planning. That is when we are trying to move an object in some direction. For example, multiple robots which are trying to catch an object and push it somewhere, or we're looking at bipedal locomotion, which is again a redundant system. Then how do you do optimization? Okay, so for example, multi-agent systems can be mobile robots, they can be manipulators, they can be multi-finger grasping. So these are all which are classified under multi-agent systems. For example, an agent in this case is a robot. Okay, so you can have a multi-fingered hand which is catching an object and rotating it. So the idea of multi-agents, also sometimes called swarm robots, has been borrowed from nature, emulating from ant colonies, beehives for motion planning. Now, I'm sure you would have noticed that if there are multiple ants, okay, maybe this is an ant, and these are ants which are carrying, you'll always find that ants will cooperate in carrying an object or pushing it somewhere. So there's an object which is to be moved like that. So the ants will go and arrange themselves around this object, either pick it up and then push it in some direction. Okay, so this is where the idea of multi-agent and swarm robotics came up from. And today we'll look at optimization for such systems. Multi-finger manipulation is another case where we have an object and we have multiple fingers which are holding the object, and we want to give a particular motion to this object. So each of these fingers can be considered to be a serial robot arm, and collectively they're doing a particular task. Okay, so kind of questions that come up here is how many fingers do you need? What is the exact positions you're going to place your fingers on, and things like that. Now the basic idea is to be able to perform a cooperative task that cannot be performed by one individual robot. So in each of these cases, like the case of an ant, in the case of these ants, one ant is too small to carry this big object and push it somewhere. So that is why there are multiple ants which are doing the task. So this is the fundamental idea in multi-agent systems where there is cooperation in performing a particular task together. Here is an example. We have a mobile robot. This is a robot that you might have been very familiar with. Some of you might have made it. So this is a two-wheel differential drive robot, and you can use these two robots if you want to push this object somewhere. Okay, so in the right hand side figure, so this is an object here, and these two robots want to push it and take it somewhere. So basically the two robots will have to go and position themselves somewhere, then push it and then take it to a particular location. So questions like how many robots are required, where they should position themselves, okay, where they should push, and things like that are something we'll look at in today's class. These are other examples of bipedal locomotion where you have bipedal robots which are carrying an object with a human, Okay, here also there is a cooperative manipulation which is taking place. Okay, robot and human cooperation. We talked about robot human cooperation in a couple of classes back. So here is a robot and a human carrying an object together. Here is a robot which is actually here. So here is a robot which is actually carrying a human now. Okay, this is two robots which are actually carrying an object and taking it somewhere. Again, the same idea where there is cooperation to do a task together. Okay. Now, multi-fingered hands. So there are many ways of grasping an object. Plus, this is something we have studied. There is the concept of force closure and there is the concept of form closure. Then depends on the kind of contact. So kind of fingertip contact that is taking place, that will determine also the kind of closure that is happening. So we know that there are multiple solutions. In all these cases we talked about, there are always very large number of solutions. Okay, for example, there are many ways of grasping an object. There are many ways by which you can give an object a particular trajectory. So this is what we are trying to look at, and hence there is a need for optimization. So whenever you have multiple solutions, then there is a question of optimization. So this is something which we'll look at in today's. This is another example that I would just like to explain to you. So this is a moving obstacle. This pink color obstacle is a moving obstacle, and these are multiple agents. Let's call them multiple mobile robots or agents. In this case, there are mobile robots which can move in any direction. Now the objective is to go and capture this object and push it somewhere. Now this object can have a trajectory. This object can be moving in space. For example, it's having some trajectory and it's moving. So you cannot go and directly try and constrain the object. Why? Because if the object is moving, you go and try and place your mobile robot here, what will happen? The object will hit that. Okay, so what is done in some such cases is that we form an outer boundary of the obstacle, as is shown by the blue line, and then the robots will first go and sit on that outer boundary. Okay, and then all of them will go together and capture the object. So the idea being that the capture takes place only when, so you can see that the pink color object is moving and the black mobile robots are first going and sitting on that outside boundary. Okay, all of them. And then once they sit on their respective positions on the boundary, then they'll go and capture the object. Okay. Now there are so many of them. You can see that some of them are going and they are getting lost also. Okay. But the idea being that you have multiple robots which will try and constrain this object, and then after it is constrained, they'll push it in some direction. Okay, that's the whole idea. Let's have a look at the video again. So this will give you an idea of, so the kind of questions that would come up here is, number one is number of robots. How many robots do you need to do this task? Okay. Number two is, where would you place them? Okay, where are you going to place around the object? Okay, and number three is pushing strategy. So we'll look at all of this, and all of this requires optimization, because as you can see that there are so many robots which are there. Do you need that many? Is there any minimum number that you require? Okay, what are the minimum positions where the robot should go and sit? Then if you want to push, do you have to change your position or it is still the same? Okay. Now let's start off with looking at grasping using 4 or 3 finger for closure. Then we'll move on to multi-agent. The idea is the theory is more or less the same. Okay, then we'll finally end with bipedal locomotion, that is walk on 3-dimensional terrain. So first we'll look at grasping using 4 or 3 fingers for closures. Now we know that there are two kinds of closures. One is form closure and then the other is force closure. Now depending on the kind of fingertip contact that you have, so depending on the contact condition, it is point contact, without friction, or with friction, or with we will decide whether it's going to be force closure or form closure. That will also determine whether you need 3 fingers or you need 4 fingers. Okay, so this is an example which we are seeing. This is the top view. This is an object and this is the circular object, and these are fingertip contacts which have been made. Okay, and this is the parrot hand which has 3 or 4 fingers. In this case, as shown on the right side figure, there are 3 fingers, so there is a range of 120 degrees between them. Okay, so the question comes that where would you place your fingers? Here, 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 here. In a circular object, of course, doesn't make it's not a bigger problem as long as you can do this kind of a grasp. Okay, but if it is an irregular shaped object, there is something we'll look at today, where are you going to place your fingers and how do you solve this problem. The same thing is applicable for mobile robots which are catching an object and pushing it somewhere. Okay, so the first thing that we're looking at today is grasping using 4 fingers, point contact without friction, and it is for firm closure. Now, the first question that turns up is, please remember that this is a computer program which will have to automatically find the solution. Okay, we have eyes, so you can look at this object shape and try and figure out where to place your fingers. That's how we catch an object. But in the case of an object with irregular figure, irregular shape, then we need to figure out where to place your fingers, and it has to be done in a program. Okay, so an object, if you take an object like this, I just take an object like this, if you see how many points, there are infinite points which are making up any side, right? So what we can do is we can basically break each of these sides into number of vertices, okay, to number of points, okay, and then we'll say that at every point the robot can go and sit there. Okay, in the case of a mobile robot or a 2-finger or multi-finger hand. So what I'm saying is that if you have an object of any shape, I need to break the boundary of that object. Say it is like this. I need to break this boundary into number of points, and on any of these points the robot finger can go and sit, or the mobile robot can go and make contact. Okay, so what I need to do is I need to make this boundary segmentation, because it cannot be infinite points. Theoretically it is infinite, but then the program cannot handle infinite points. So basically I'm going to break the boundary into a number of discrete points. Okay, so the whole idea is boundary segmentation for discrete points. Okay, and how do we do that? So we take this, I know the vertices of this object that we are seeing here. So these are the vertices I know. So what I can do is I can break each side. So I divide each side into fixed length, divide this by a fixed length, so this much, this much, this much, and see how many points I can make there. Okay, so whatever is the length, and if a robot sits there, now I know that if I start from 1 2 3 4 5 6, okay, so I'm breaking it up into the more number of divisions you make, the better result you will get, in the sense that an object, a mobile robot can go and sit in more places. However, your computational cost will go up. Okay, so you cannot make very large number of divisions. So if you make a fair number of divisions, say in this case, and start numbering from 1, so this is my 1, that's my 2 3 4 5 6, like that. Okay, so in this case, wherever the robot is going and sitting, we can name that as 1, and wherever it is not sitting, we can name that as 0. So wherever, on whichever point the robot is present, we name that as 1, and wherever the robot is absent, we name that as 0. And we make this binary string. So this is going from 1 to, there are how many total points? 20, 21, 22, 23, 24. There are 24 points here. So I make this binary string of 24 bits, and the bit can either be 1 or it can be 0. Okay, so if a robot is present there, it is 1, and if a robot is absent, it is 0. Now the total number of robots, like in this case, 1 2 3 4 5 are there. Okay, there are 5 robots here. So this string is basically giving you an idea of this object, and this is the string that I'm going to play with using genetic algorithms for optimization. Okay, so this is basically converting an analog problem in the real world to the digital world by using discrete points and in the form of this binary string. And this binary string, if you just look at it, it's very interesting and very clear that how many robots are there. Yeah, so there are 5. Wherever there is a 1, there's a 1 here, 1 here, 1 here, 1 here, 1 here. So there are 5 of them, which means that there are 5 robots, and the others are 0. Okay, and which position is also clear, because I'm going to number them like this clockwise. So this is 1, this is 1 2 3 4 5 6, the next one is 6, so it is on 6. So by looking at the number of the bit, I also know exactly where the robot is present. Okay, so this is how I'm going to do my object boundary segmentation, and basically what we're going to play with is we are going to use this binary string. So basically, if I just explain very briefly or in a very simple way, that what GA will do is it will change the positions of these ones randomly. Okay, so at different ones, it has a total of 5 ones. So it'll keep changing the position of ones randomly, and then see what is the cost function. Okay, and with constraints. So if this one is 1, the next one it'll make that one make this 0. Okay, so that is what it does, and that is exactly how we are going to proceed. Okay, now if you want to satisfy a grasp, we need to have satisfy the conditions of placement of the fingers. Where are you going to place your fingers? Okay, so we can have objectives like the finger should be placed such that the clockwise and the anti-clockwise moments are the same. That makes sense. So if you have an object like this, if there are two fingers which are pushing like this, there is one finger pushing here, then there has to be one opposing this side, and if there is one here, if there is one here, there has to be one on the opposing side there. Okay, so basically what we are saying is that if there are opposing moments which are there, then that gives you the best solution, right? So what we are saying is we are going to maximize we are going to place our fingers such that the counterclockwise moments and anti-clockwise moments balance each other, or we are going to maximize this. Second is we are going to minimize the angle at the center. What is theta? Theta is the angle subtended at the center. So if this is the CG of the object, then this is the angle. If I place a finger here, this is the surface normal. So whatever is that angle, theta 1, theta 3 in this case, I'm going to try and minimize the sigma of. So in this case, it will be minimization of sigma 1 plus theta 1 plus theta 2 plus theta 3 plus theta 4. Okay, that is what we are going to minimize here. Now, why is that important, or why is it required? This is required because if the normals are pointing towards the CG, the grasp is more stable, right? So if you have an object like this and the grasps are going through the CG point like this, then this is the most stable configuration. Okay, so this is one. The second is we can talk about there should be robots creating movements in both the directions. Okay, there should be clockwise and anti-clockwise movements, both should be there. So if you only have clockwise movements, it is not going to work. Okay, say for example in this case we have one here, one here, and one here. So this one is going to cause anti-clockwise, that will cause this side, this will cause this side. So there are moments on all sides. Whereas in this case, the moments are all in this side. Okay, so moments are all counterclockwise. Sorry, this is clockwise moments. Now this is not stable because it is going to simply rotate the object. Now where are we getting that from? That we are getting from sigma f is equal to 0 and sigma m is equal to 0. So which means that the sum of the forces and sum of the moments must be equal to 0. So this is what we are talking about. That now, is there any other constraint? So the other constraint that we can have is other constraints that are required. One is that the moment should be clockwise and anti-clockwise. The other constraints are that the fingers should not overlap. There should not be one finger sitting on top of another finger. The total number of fingers should be 4. This we are minimizing. You can leave it. We'll just come to the other problem where we have multiple mobile robots. In that case, we also have to optimize the number of robots. In this particular case, we are simply saying that we have 4 and we have 4 fingers, and so the number is fixed. The area formed by the fingertip contact is non-zero, and the number of fingers producing clockwise and anti-clockwise moments are equal, and accessibility angle is 0. Okay, now, so the first are very clear. There are 4 fingers. You have clockwise and anti-clockwise moment. Both are there, and accessibility angle is 0. Now, what is this accessibility angle? Now, accessibility angle basically tells you if the object has been captured or it can still have degrees of freedom so that it can move in a particular direction. Okay, so what we are seeing is that it is like this. If I have an object here, an object here, a finger here. Now, although you have these fingers, 3 fingers, this object is still free to move in that direction. So unless I place a finger there, the finger will not be constrained. So this constraint is required for form closure. Is required for closure. Now, closure basically means that the object cannot escape in any direction. That is the meaning of closure. Okay, and now we are talking about a computer program. So how are we going to ensure that the object cannot escape in any direction? Now, if you just go back a little bit, when we talked about the binary string, now this string basically tells us where is the location of the fingers. Okay, based on that, I can compute my clockwise and anti-clockwise moments. Now, I also need to compute if the object can escape or the object cannot escape. Okay, if the object can escape, then the grasp is of no use. Or if there are multiple robots trying to catch an object, it's of no use because the object can escape. Right, and how do you do that? So we talk about the concept of visibility angle or freedom angle, and it's very simple to understand. So if you have an object here, let's look at this figure, and you place a fingertip here or a mobile robot there. Okay, now it basically means that if I put a fingertip here or a mobile robot, there's a normal force here, and this surface is flat. So the object cannot move in this direction, but can move in that direction. So this is not, cannot move this side, it can still move. Okay, so it basically says if you place a finger, there is the concept of freedom angle. Freedom angle means the direction in which it can move. Now what is the freedom angle? It is this angle. This object can move in that direction fully. Okay, so if I combine all the fingertips like this, I draw this graph on the right side as shown here. Now for this finger, this is my line, okay, for finger number 4. So it is basically saying that this line is this line now, and this is the freedom angle for 4. Okay, so I'll just change the color, and then we understand. For 1, this is the surface, and this is the finger, the freedom angle. That means in that direction it can move. So this is 1, and this is the freedom angle for contact 1. What about freedom angle for contact 3? Freedom angle for contact 3 is this one. So this is 3, and this is my 3. Okay, now if you combine all of them, 1, 2, 1, 3, and 4, is there any angle which is left uncovered? So we know that total is 360 degrees. So is there some angle which is left uncovered? And that is basically what we see, is that this angle here is left uncovered. That means if you place 3 fingers in locations 1, 3, and 4, then the object can still escape in this direction, in this region. That means the object can still go off in this direction. Okay, and you can stop it only by placing one more finger that is shown here. So that basically means that you have to place your, in one more direction, you have to place your finger. Okay, so it basically means that this is the area which, this is the angle which is not covered, and I need to place a finger such that this angle is also covered, and that is what is done here. Okay, so I place a finger here now, so this gives me this line 2, and this is my line 2, and now this is also covered, okay, as shown in this figure here. So this is how we can figure out, is there a possibility for the object to escape in some direction, or the object has been completely constrained. So a program has to actually do this. So it takes the binary string, finds out the location of those fingers, draws the visibility angle, and then it can compute if you're covering 360 degrees or not. Now that is also pretty simple. If you take any side like this, let me just explain it. So I have a point here, I have a point here, I have a point here. So I take the normal here, okay, and I take the next point, I take these are vectors, so I can basically compute the angle between this and this, and that is my freedom angle, right? So as shown here, okay, so for any Ri, there is a Ri plus 1 and Ri minus 1. Okay, so if this is my Ri, then there is an Ri minus 1, and there is an Ri plus 1. Okay, and that is what we are seeing in this particular case. So the computer can also check if the object can escape in any direction, and this is also a constraint. So we have seen that we have now the constraint of accessibility angle, that the accessibility angle should be 0, which basically means that no angle is left uncovered for the robot to move, and then we know that the object is captured. Then the next question would come, where would you place your fingers? Okay, where would you place your fingers? And that we have seen that we have to use some kind of optimization. Let's see. So we have our binary string, which is 0 1 0 0 0 1 0 0 0 1 0 0 0 1 0 0. Okay, but which we have got by segmenting our object boundary, making it into a digital boundary. Now what GA or genetic algorithms basically does is it generates a very large number of pool of solutions and ranks them as per the objective functions. Now how does it generate a very large pool? It will take this binary string and randomly change, well, not randomly, there are ways, there is mutation and crossover which is done. We don't have to worry too much about it. What it basically does is it changes the position of the ones and zeros. Okay, so this is 0, this becomes 1 0 0 like that. Okay, it can do it randomly, or it can do by using crossover and mutation in a particular way, but it generates a very large pool of solutions. Then it checks. So number 1 is a very large pool of solutions are generated. Okay, then number 2, it rejects solutions that do not satisfy the constraints. For example, if it gets a solution in which if it generates a solution in which it finds that the accessibility angle is not satisfying, then it will just reject that solution. Then number 3 is it ranks the solutions in terms of objective functions. Whatever is the cost function, what are you trying to maximize or what are you trying to minimize? In the case of bipedal locomotion, we said that we are trying to minimize energy. Okay, in this case, what are you trying to maximize or minimize? So the objective again can be multi-objective. You can have more than one objective, or it can be single objective. Okay, so these are basically in optimization. You can have single objective, or you can have multiple objectives. Now, in a single objective, there is one objective, as the name indicates. So it can be a combination of the clockwise, anti-clockwise movement. It can be number of robots. In case of multi-objectives, you can have more than one objective. So you'll get multiple solutions again. Okay. So first, we try to solve this problem using multi-objective optimization. And here, what we see is that this is the sum of the angles, and this is the sum of the moments. We talked about sum of moments, sigma m. And this was the first objective. The second objective was sigma theta. That's something we looked at. So if you look at this sigma m and sigma theta, okay, what we see is that, so what we're seeing is that the number of solutions again depend on the two objectives. And for example, if you're giving more weightage to sum of angles, then your solutions are, these are the solutions that are optimal. If you're giving more weightage to some of the angles. If you're giving more weightage to some of the moments, then this is the solution that is optimal. Okay, so normally we would go somewhere in the middle and say that this is probably the region where we are looking at. So that is probably the solution that we will choose. Okay, for each of those cases, 1, 2, 3, 4 that are marked, the figures are shown here. The placement of the fingers are, or mobile robots are shown there. Okay, so this is effectively how we find optimization solutions. In this case, it is for multi-objective optimization. In the case of this star-shaped figure, exactly same problem. We have 4 robots. We have 4 robots or 4 fingers. And we have the objectives are sigma theta and sigma moments. Okay. So we see the sum of angles are this side and some of the moments are that side. Yes, and if you're taking more weightage, if you're giving more weightage to sum of angles, then these are your solutions. And if you're giving more weightage to sum of moments, then these are your solutions. Again, we can take somewhere here and say that this is having equal weightage to both of the objectives. Okay. Now, we talked about form closure. Let's look at force closure. Now, this is not only for multi-fingered hands, this is also for mobile robots, because exactly the same thing applies. Now, let's look at force closure using 3 fingers. We can say 3 fingers or 3 robots. 3 mobile robots. Okay. Now in this case, the objectives can be maximum area of the triangles. So I have 3 fingers. Force closure is point contact plus friction. Okay. So in this particular case, we have 3 fingers. We have point contact with friction, and the objective can be maximum area of triangle. So we have maximum area of the triangle, which is here. Okay, so we place our 3 fingers like this, and this is the area of the triangle. We try and maximize the area of the triangle. How does it help? It is more stable. Okay, so if you have an object like this, if you catch it here, here, and here, it will be more stable if the area of the triangle made by these 3 angles like this, by these 3 contact points, is maximized. So if I have here, here, and here, this area is bigger, right? So this will be more stable as compared to that small triangle which is being made here. Okay, so that is why we need to maximize the area of the triangle. The minimize force focus, that is theta, we talked about. Minimize force focus is we have at every point, if I have a fingertip here, then there is friction there. So there is a friction cone. Now the friction cones intersect and they have this area there, which is the intersection of all the friction cones. Now, whatever is the, so in this friction cone, in that area where we have the friction cone, we also have the CG of the object, right? So if I take the center of this and the center of the CG, that distance, so I call that distance D. Now that is basically what I mean by force focus. So if the forces are directed towards the CG of the object, then it is known that the object is, the grasp is stable. Okay. So the second objective is minimum force focus, and the third is force line, which is my sigma, which is minimization of the angle which is subtended at the center. Okay, so we have maximum area of triangle minimum force focus, and force line minimum theta. All these three we are trying to maximize. Now the constraints are, there are three fingers. Friction cone should be satisfied. That means the normal force should be inside the friction cone. That has to be satisfied. Okay. Then obviously the escape angle should be closed also, so it cannot escape. So there are three objectives here. So we have done multi-objective with these three of them, and as you can see that now we have three of the solution graphs. So these are what I call Pareto fronts. Okay, or Pareto solution sets. Now because there are three objectives, we have a 3D kind of a graph. So here it is force line versus area of triangle. Here it is force line versus force focus. Okay, and depending on which weightage you're giving, how much higher weightage you're giving to which of these objectives, you can choose a particular solution. Okay. So in this particular case, we are seeing the case of 1, 2, 3, 4, which is indicated here. So there is one where we are placing finger here, here, and there. Another case I'm placing here, here, and here. So these are all optimal solutions depending on which weightage is having a higher value, A or D or theta. So you can choose, but they are all optimal solutions. So in such cases, you cannot talk about which is the best solution, because this is a multi-objective now. Depending on your objective, your solution is going to change. Now, best solutions for different cases. These are some examples where we have looked at different shapes and we have found the different solutions. Okay. Now we can talk in terms of single objective. We talked of multi-objectives where you have multiple solutions. Okay, so multiple. Okay, now we can have multi-objective where you can have more than one objective, or you can have single objective. Okay, so now we'll talk about single objective optimization for a number of robots. For example, if I'm trying to optimize the number of robots also. Okay, in the case of the video that we saw, there are a lot of robots which are moving around. There are a very large number was there. Okay, so now suppose I want to minimize the number of robots also, then I can put that in the objective function itself. Now if you do single objective optimization, it will be something like this. Again, the same, whether the number of robots when it is capturing an object should have clockwise movement and anti-clockwise movement. Okay, so this constraint takes care of rotational inaccessibility. Okay, that means that it should have both clockwise and anti-clockwise moments. Now the objective function can be something like this. Now please note that there is no unique objective. There is no unique objective function. Okay, there is nothing like a unique. It depends on what objective function you are trying to use. You can change and play with the parameters. So in this case, what we are maximizing is the clockwise moment plus the anti-clockwise moments. Okay, we want to maximize. Then I'm saying it is divided by n raised to k, where n is the total number of robots. Okay, so here the variable is also the total number of robots. So in that binary string, we're going to start playing with the number of robots also. Okay, so the number of ones and the number of zeros also will keep changing. Okay, so the number of ones can be more than 4. So this is the first into 1 by moment clockwise. So number of robots sitting counterclockwise and the number of robots sitting clockwise. Okay, so we want the robots to sit in produce clockwise moment as well as to produce anti-clockwise moment, so that they are distributed properly as shown in this figure. Otherwise, what can happen? All the robots will go and sit here. Okay, this side there is no robots. Okay, to avoid that, what we are doing is we are saying that the number of robots producing clockwise and anti-clockwise moment should be 0. That means they're equal. Now if this becomes 0, then this will become infinity. So we are adding a very small positive number. Okay, small number, so that it does not become infinity. Otherwise, if NCW becomes equal to NCCW, then this will become 0 and F will become infinity. Okay, so if you do this optimization again, in this case, please note that N is the number of robots. So I'm also changing the number of ones which are there. If you do that, very interestingly, what you find in the solution is that it comes down to 4 robots only. Okay, so this is very, very interesting that whatever we have learned in terms of form closure, force closure is applicable. Even with optimization, you can get the same result. So if you optimize it here, what we are getting is in this particular case also, we are getting that the optimal solution has 4 robots only. Okay, so this is a moving object. You can see obstacle avoidance and capture of an object. So these are obstacles, and this is the object it wants to capture. This object is rotating with a circular object, circular trajectory. So you can see the black line which is going around like this, and it is going around like this. Okay, So what we are saying is that the optimization actually shows that you need minimum 4 objects for form closure. Okay, this is something we know from before. And if it goes and catches the object, it can actually go and avoid the obstacle. These are obstacles it can avoid. Then it goes and sits on the boundary of the obstacle. Okay, and once all 4 of them have sat on the boundary, then they go and capture the object. Okay, that is how it works. And this is also a single objective way of doing. Now you can actually put different objectives. So you can put different objectives and try and look at. Okay, so this is, as I said, that you can look at different objectives and okay. So now next what we look at is pushing an object. Now we have captured an object. Okay, in this figure we have seen that we are able to capture the object. Now I want to push the object to some destination. Okay, how do you do that? After the object is caught, so if this is my object, the object has been caught, okay, by mobile robots or multi-fingered hand. Now I want to push it in this direction. Okay. Now if you want to push it, these two fellows cannot be there because they will start obstructing the motion. So this position, they have to reposition themselves and come somewhere this side. Okay, so now each of the mobile robot is projected a few instances ahead and then check for collision. So this is my mobile robot. Okay, so what is done is we do projection. So the robot is going to have some velocity like this, and the robot is applying a force in that direction. Okay, so what we are seeing here is that what we are doing is first we have to realign our objects. Okay, we have to realign our robot, and then we have to place our robot such that it goes and actually pushes in a particular direction. So optimal pushing of the object to the desired goal point. So the robots are reoriented for optimal pushing by switching between passive and active robots. Now what is this passive and active? Now these are the active robots which are applying a force, and these are the passive fellows which are simply moving or following. Either they are not there, or even if they are there, they are not pushing. Okay, they are just following. So the idea being that you push this object in this particular direction by placing these two robots only here. Okay, now if you push, if you say this is applying force F1, this is also applying force F1, then there will be a resultant force in some direction and the object will move towards the resultant. Now the resultant need not be in this direction. So basically what we have to do is we have to alternately push such that the resultant motion is in that direction. Okay, I hope you follow what I'm saying. Suppose I have an object like this. So this is my object. And this is one robot here which is placed, and this is another robot which is placed here. Okay, so these are all normal. These are normal. Now suppose I'm going to push. Now if I'm going to push, then what is going to happen? The motion of the object will be this side first. Okay, then if this is pushing, then the next one is pushing. So this is 1 and this is 2. So when 2 is pushing, it is going this side. Then again 1 is pushing, then again 2 is pushing. So it is going in the zigzag path, but the net resultant is in this direction. Okay, so you have to divide your net resultant such that it is an average of the zigzag motion that we are getting. So this is my net resultant motion. Okay, so this is how we are doing the optimization. So we have these robots which have reoriented themselves, and these are the two active robots, and I take a D dot of F1, F2, F3, and I try and maximize this. D is the desired direction, and dot of F is the forces F1, F2, F3 which is there. So I try and maximize this, and the result of this is that we end up moving in again I can use optimization using genetic algorithms. Why use genetic algorithms? If some of you are wondering, then because it is played strings, and it's very easy to represent this object boundary using this kind of string, and that is the reason we're using this genetic algorithm based optimization. Okay, so in this particular case there are 4 robots which are sitting, okay, in these positions, and we're going to push in such a way that the resultant of the object is in the desired direction. So 2 of them will push, then another 2 will push. Okay, and the resultant of this is going to be in a particular direction. For example, this. So we are seeing that moves like this, like this, like this, like this, like this, like this, like this. Okay, so first maybe this will push, then maybe this and this will push. Okay, so it will continue that way, and then finally it is going to go in the resultant direction. So that means F or D dot F is what we are maximizing. So which robot is going to push will be determined from here. Okay, that is the above equation that we have seen. from this equation. So which one is going to push will be determined by maximizing this. So this is an example also of optimization of multi-agents, which can also be looked at mobile robots or can also be looked as fingertips. Okay, and this is how it operates. Now let's look at just look at the other problem that we were looking at, that is in bipedal locomotion. Okay, so let us go straight to bipedal locomotion. We talked to bipedal locomotion. Let's talk about bipedal locomotion in so we talked about bipedal locomotion. We talked about zero movement point. Okay, and we talked about so very briefly again, very quickly explaining that we know that there is a zero moment point, and for balance you need to maintain your zero moment point, right? So this is a video which we had seen in the previous class, that when the robot is walking, the zero moment point should be on the foot perimeter, right? Now okay, let us just move forward. Okay, so we are here, and we said that when a biped robot walks on flat ground, then there are infinite trajectories which are possible. So there is a leg trajectory and there is a hip trajectory, and in the last class we looked at how to optimize the leg trajectory and the hip trajectory and minimize the torque, which is tau is equal to energy is equal to tau into d theta dt. Okay, so this is the total energy that is being consumed. Okay, so this is the energy that is being consumed, and based on that we find the leg trajectory which is best. Now let us look at the a little bit more tricky situation, and this is something we have discussed in the last class also. These things have been discussed, that you use DH parameters and put the frames. So this is an 8 degree of freedom biped robot. Now 8 degree of freedom basically can walk straight, it cannot turn, it cannot go on 3D, it can only go on flat ground, it can walk straight. Okay, so please note that 8 degree of freedom can only walk straight, and number 2, it can walk straight and cannot turn and cannot go on 3D terrain. Okay, so if you want to go on 3D terrain, basically you have to increase your degrees of freedom. So from 8 degrees of freedom we are increasing to 14 degrees of freedom. So this is a 14 degree of freedom system in which there is 7 degrees of freedom. Okay, so there are 3 degrees of freedom at the ankle, 3 degrees of freedom at the hip, and 1 degree of freedom at the knee. Sorry, 7. Okay, now in this particular case the procedure is exactly the same. You make your DH parameter table as shown here, and then write your dynamic equations and kinematic equations. But now the problem becomes more complicated, a little bit more tricky, because you're on 3-dimensional terrain now. Okay, so this basically means that we have to optimize the foot trajectory, and we have to also ensure balance. Okay, so basically what we have done, or what you can do, is that basically we can try and to make matters worse, what we are saying is that even the leg, the step length can be a variable now. So we have this many variables. P1 represents the x coordinate of mid of hip, P2 is the y coordinate of hip, then P3 represents the z coordinate of hip. Okay, so x, y, z coordinates of foot is here, height of foot is given here, and x coordinate of mid hip and is given here. So basically what we are saying is that we are trying to control the hip trajectory using these parameters. Okay, and we can do our dynamics. This is the Newton-Euler dynamics which you have studied earlier. Procedure is exactly the same. We are again going to optimize and minimize the energy or the work done. Okay, so I have to find the torque, and I have to find from this equation. Now the problem comes in the sense that it's very easy to talk about balance when you're in 2D. The moment you're in 3D, then there becomes a problem. Okay, so in case of 3D, what we have to do is we need to look at the normal vector of the supporting foot surface. Say for example, if your foot is here, so one foot is placed, so one of your feet are here, okay, and your other foot is here now. Okay, so in this case the normal is in this side, here the normal is in this side. Okay, So what we can do is we can try and ensure balance. One way is by using a projection method by which we project. Suppose I project this onto the ground like this. Okay, so I make the vector this side and then see whether the 0 1 point is inside the full perimeter. That is one way of solving it. The other way of solving it is by taking an average plane in between. I can take an average plane somewhere in between and then see if the 0 1 point is being satisfied. Okay, so that needs to be done for the case of three-dimensional terrain. Now the problem here is that there are too many variables now. In the previous case you were just playing with the ankle trajectory or the hip trajectory. Now the ankle trajectory also depends on the terrain you're walking on now. In the previous case it was flat, so that problem was not there. Now it is 3D. What is the meaning of 3D? 3D basically means that this is one. If I put my grid map like this, then this is a grid map. Okay, so if you're having a grid map like this, then there are vectors on each one of this, and these vectors can be in any direction. That is the meaning of a grid map. Okay, so this, what we need to look at is the vector on that grid. Okay, that will depend on the angle that grid is making with the three axes. So if you place your foot here, or if you place your foot here now, the trajectory is going to be different. Okay, that is expected, right? Now if you want to optimize, you can have this alpha, the angle can be infinitely many. So basically what is done is we have to make a very big database. So it cannot be done very simply like optimization, which we did in the last class. Okay, now in this particular case we make a very big database. That means you start finding optimal trajectories, optimal leg and foot trajectories for different terrain conditions. Okay, so find optimal foot and leg trajectories. Okay, for different terrain conditions. Okay, so for different terrain conditions. And how do we do that? For example, if I know that the robot is going up and there is an inclination up in the upward direction, I start finding trajectories for different angles. So I take, say, 2 degrees, 4 degrees, 6 degrees, like that. And for each of this I find trajectories. If it is going down, again the same thing. Okay, alpha is equal to find trajectories, and make a database like this. Now this takes a lot, because each optimization will take you minutes, if not hours, and to generate a database like this covering all kinds of terrain condition will probably take you days. Once you have made this database, now we have to train some kind of learning algorithm. In our case, we have simply used neural net. So it basically means that there is going to be, given the angle of the terrain, it can find out what is the suitable trajectory that is optimal for that angle. That's what this is doing. Okay, and if there is some trajectory in between, then it can interpolate. What does that mean? That because I have taken alpha is equal to 2 degrees and then 4 degrees, suppose there is 3 degree terrain now what it will do? It has to interpolate the trajectory. Okay, so once you train something like a neural net, that can do it very easily. And what we have seen is that this is an example where it is walking on different kinds of terrain, and it can so this is an example of the robot which is walking on different kinds of terrain, and it has been learnt. So the various depending on the inclination of the normal of that particular grid and the corresponding the foot trajectory which has been learnt. Now the robot, as you can see here, is can walk. So the robot can walk very slowly. As you can see that it is walking and going. This is three-dimensional terrain. So each of those grid markers are having different normals. In the case of the flat ground, it is always pointing upward. Here it can be in any direction, but it is having optimal walk. Now once you have learnt it, it can be done in real time. Okay, so this was an example where you can make a data set of biped walk on different kinds of terrain conditions, and then the robot can walk on the terrain in real time. So today we end here. And this is the last lecture of the course. I hope you enjoyed the course where we tried to cover the basics and advanced topics in robotics, and then finally looked at some advanced research topics like bipedal locomotion, optimization, multi-finger grasping. I hope it has been useful to all of you, those of you doing research or in industry. Now, those of you taking the exam, I wish you all the best, and I hope you'll be taking some more courses of robotics in NPTEL. Thank you.